Hello, and welcome to the Disrupting PFAS podcast. I'm your host, Jeff Hale. For this season of the podcast, I have curated 4 episodes focusing on the detection, destruction, and sequestration of PFAS using novel materials or processes. Today, I will be talking with Dr. Radha Motkuri of Pacific Northwest National Laboratory about PFAS detection, capture, and destruction using nanoporous materials. This is a very fitting topic for the podcast as it covers all the elements of our theme, detection, capture, and destruction, as well as novel nanoporous material. So let's learn more about the technology from one of its innovators. Welcome to the podcast, Radha.
Thank you, Jeff.
So we're honored to have a researcher from Pacific Northwest National Lab join us on the podcast today. Could you please tell me more about the mission of Pacific Northwest National Lab, which I'll refer to as PNNL, and the type of work being done there?
Great, thank you. The PNNL, Pacific Northwest National Laboratory, is one of the DOE national laboratories located in the northwest part of the US in Washington state. So this is a national lab. We are working on various science missions like NSD, national security, science, environment, energy, and all the aspects. Roughly, we have more than $1 billion of revenue every year, and with more than 5,000 staff working at PNNL on various missions, including national security, science, and also other aspects.
Excellent. So we're really glad to have a representative from PNNL on the podcast today, as I mentioned. Could you tell us about your role at the lab, please?
Yeah, I'm a material scientist and a chemical engineer at PNNL, and I joined almost 13 years back, in 2008. Basically, I am a PhD in material science and material chemistry specifically, working on the nanoporous materials, or zeolites or mesoporous silica at that time before my joining at PNNL. So after joining the PNNL, mostly worked on how to utilize these nanoporous materials for real world applications. Basically started in 2010, we got a project on the adsorption cooling, where utilizing the heat evolved or heat generated during the process of adsorption and desorption of a guest molecule to the host of nanoporous material that we utilized for energy the adsorption, cooling, and refrigeration applications. At that time, we used refrigerants such as fluorocarbon-based refrigerants. Those refrigerants helped us to go into the PFAS science, because the fluorocarbon is the same fluorocarbon in PFAS too. So that's the close relation where we have the nanoporous material chemistry and the PFAS chemistry.
Excellent. So that's an exciting field of research and very interesting on how it progressed. Could you tell us more about nanoporous materials? What are they? How do they, some of their unique properties and how they play into this field?
Sure, definitely. So a simple example I'll start with, when you purchase an electronics, generally you find a small sachet inside an electronic box, right? When you, they clearly say that don't eat, but do you know what is the purpose of the sachet? It is for taking the moisture in the box to keep the electronics safe for longer duration in the transportation, right? Until to reach the customer. So that is a nanoporous material, which is simple silica. Its role is to take out the moisture in the box throughout the packing to shipping to the customer. So that is one kind of nanoporous material, simple silica. And an analogy, and there are so many nanoporous materials are existing in the literature, like zeolites, mesoporous silica, metal organic frameworks, covalent organic frameworks, or various kind of nanoporous materials are existing. I think people might know zeolites are very famous as nanoporous materials, right? they have invented or discovered like a couple of decades back, a couple of centuries back. And so those are the nanoporous materials. And one thing is that the nanoporous material that we are using, that we an analogy I given in a electronic box, right? That's simple silica gel having SiO, SiR, SiOAl bonding, where that role is only taking the water molecules. But recently, like 20 years back, like there is a development of metal organic frameworks. The metal organic frameworks are similar to that of zeolites structures, where the zeolites having silica, oxygen, alumina bonds, but where nanoporous materials of MOFs, metal organic frameworks, have metal and organic linker and forming a structure. So it is like, for example, another example is like a sponge kind of material. Okay, the sponge, just you can just take a sponge and put in the water, it will suck all the water, right? This is, you can see by visually, you can see what's happening. But at nanoscale, the same, if you the nanoporous material is like actually like a sponge at nano level, where it looks like simple white powder or some colored powder, but its role is will act as a sponge kind of material.
Well, that's a great description of nanoporous materials. I'm not sure everyone is particularly aware of what they are and what they do. So I think that'll be a great foundation for when we talk more about the technology you've been working on. I wanted to bring it back to PFAS for a minute. So you described how you arrived at doing some PFAS research with these materials. It grew out of looking at refrigerants. As a researcher, as a technologist, what is your outlook on our ability to tackle this human-made contaminant with technology?
The problem is very big. The PFAS problem is a huge problem. And only material chemists are not sufficient. We have to have a combination of like various fields of science, engineering, like all those things has to come together to bring a technology that can work to complete remediation of PFAS. So for example, right now I'm working with an electrical engineer in the for the prototyping. I'm working with a mechanical engineer, working with chemical engineers, material scientists, and and finally we have to work with the medicinal people, where the health effects people will work. So it's like all the fields has to come together to tackle this problem.
I want to start getting more into your research and the technologies that are being developed at PNNL. The first thing you mentioned was detection. There's a lot of focus on treatment, remediation, destruction of PFAS compounds, but it's really important to know where they are and at what concentration, and to know that information rapidly. So understand PNNL has developed a Fast PFAS Sensor using these nanoporous materials. So can you talk about how nanoporous materials are used to detect PFAS?
Wonderful. So that maybe before going into the topic directly, I will give a brief background of nanoporous material, which I mentioned in a previous question. When we are doing the nanoporous materials from last decade on the fluorocarbon-based adsorption, we really understood what is the role of the fluorocarbon inside the pore. Because the pore, nanopore, the pore porosity, surface area, pore volume, and metal centers, functionalization, all those things will be having a role on the absorption of this PFAS or the fluorine containing molecule. For me, PFAS is a molecule, a fluorine containing molecule, right? All I look is how the fluorine containing molecule is having a role inside my pore, the nanopore of the mouth. Whether this is having a chemical bond or physical bond, more attraction, less attraction, how can I tune the attraction of this host of nanoporous material and the guest of the fluorine containing molecule. So we established a various studies do the like expensive experimentation, like for example exhaust, zanes, in situ studies like IR, FTIR, or various studies we have done on the fluorine containing molecules inside the nanopore material. What is the interaction strength? How can we increase the strength between the host and guest? How can we decrease? How can manipulate? How can we tune the strength between the host and guest from over the 10 years, right? So once we changed our gears to PFAS, because again I'm looking this one as a fluorine containing molecule, whether fluorocarbon or 134A or the fluorocarbon or PFAS are the same kind of molecules, seek alkyl chains with the fluorines, right? Number of fluorines. So in that space, I will see more adding number of fluorines on the PFAS, how they are interacting into my pore. That helped us, okay, this is the methodology that we can tune the material into construct into this kind of a structure may be helpful for the PFAS.
So if I could bring that back to an analogy that you gave before, you talked about the nanoporous materials is almost like a sponge. So it's got a lot of nooks and crannies and pores in there. And so molecules, in this case PFAS, would basically get nestled in to the pores and pits and nooks and crannies of the sponge or the nanoporous material. And but they can kind of sit nestled in there in different ways that you can maybe exploit to understand or gain information from how that molecule is sitting in that nanoporous material. Is that a good analogy or summary?
Yes, that's right. But the in a sponge kind of a thing, the water just you push it out and bring it back easy, right? The same thing here, but there is some driving forces required to get them out and get them in, because the driving force has to be there, right? Because there are so many molecules in the water, right? So all the water can go into the nanoporous material, but why why can only PFAS can stay there? All the molecules can stay, fill the complete material, and there's no space for other PFAS molecules.
Good point.
So we have to engineer the nanoporous material, specifically designing the fluorophilicity in the material. Fluorophilicity means the so you know hydrophilicity, right? The material hydrophilic in nature, meaning that water attracting. Similarly, we have to design the material, develop the material that is super fluorophilicity, meaning that only attracting towards the fluorine containing molecules. Then when you put in the water, there are so many other contaminants, so many other things are there around, but it's more specific to can extract only the fluorine containing molecules.
Fascinating. Excellent discussion, Radha, about nanoporous materials and how they're used in PFAS research. Can you tell us more about these materials and their adsorption characteristics and how they interact with these types of molecules?
Yeah, that's a good question. So the nanoporous materials, there are different kinds of nanoporous materials are there, and basically, as I said, I did my PhD in zeolites zeolites type of materials as nanoporous materials, but as turned into the metal organic frameworks or covalent organic frameworks or porous carbons. I can show you an example, like a slide where different kinds of nanoporous materials are present. Say, for example, here you can see the metal organic frameworks, covalent organic frameworks, and porous carbon, hierarchical porous carbons, and nanoporous silica and zeolite materials. So the difference here is that if you look at with naked eye, you can see all of them as a powders. You don't differentiate. If I give you a powder of MAF, a powder of zeolite, you cannot see a differentiation because those are all powders. But when you look with a microscope, then what happens is that how the pores are built, what are the pores connected with, which are like how the pores are connected, how the orientation, everything matters. Say, as I told in the beginning, like the construction of an airport is different from a school or hospital, right? Same thing here at nanoporous material. This type of a structure here is completely different behavior for different this kind of structure at nano level, because when the molecule enter into the here, and enter and exit may be very easy because it looks very like a tubic kind of structure, whereas if the structure is like different kind, the time it will take go into the structure and come back is late. For example, how much time do you take to go into an auditorium and come out? Maybe few minutes. But the same thing, 10 floor, the same space of the auditorium area wise, but you have a 10 all the rooms. How much time does it take for you to go into the middle of the room and come back? It's a longer time. Same thing, the molecule, the chemical molecule, the molecule go into the space, how easily it will go into space, and then how easily attracts to that pore. Structure is also important, right? If there is a good show, or if there's a school or somewhere where you have a movie going on there, you have more attraction. You sit there and not rather than something, right?
Mm-hmm.
Similarly,
Good
we have
analogy.
yeah, so we have some good functionality here where the molecule can sit in with a wonderful source of attraction or some chemical attraction between the host and guest to create, so that we can have pull all those molecules into the pore. And these are different kind of fluorine containing molecules, fluorocarbons we studied, and the difference between those and here is only the difference is like having more number of fluorines and longer chains. So the PFAS are from starting from even four membered, like butane or PFBA kind of material, to all the way to 12, 14. So having number of fluorines, so now increasing the fluorine content here on the structure, then how can we have more interaction or more functionality here in the pore to get more PFAS? That is a host and guest relationship, and how we can improve the relationship is a part of my duty to for engaging for my duty to improve the technology, improve the adsorption capacity between the host and guest.
So I think that's a fascinating discussion of nanoporous materials. I liked what you talked about, the host-guest relationship, how PFAS or other molecules get, nestled in the pore space of these nanoporous materials, and you're working to fine-tune, improve that relationship, that host-guest relationship, to exploit it for some sort of practical functionalization, which is what I wanted to talk about next. We're talking about the detection of PFAS using this host-guest relationship in nanoporous materials. Could you talk to us about the architecture of the sensor itself?
Oh, wonderful. So as I mentioned about this capture mechanism, how the host guest interactions are happening, right? With the simple host guest interaction, we cannot go for the detection limit of parts per trillion. We may go up to like only parts per million level or higher. So we, in collaboration with New Jersey Institute of Technology and JIT, Professor Sagnik Basure, who has a technology of microfluidic impedance analysis, and he was using for some other like blood cells or some other biological work. By combining, when we discussed together, we combined our technologies of these nanoporous materials, the microfluidic device, and then impedance analyzer together, brought into one factor to bring the detection mechanism. I'll explain you how I can show you something that how it can clearly see um, the detection mechanism here. So how the overall detection PFAS, PNNL PFAS sensor or detection works. This is a kind of a device where we can have a chip. A simple example is like a glucose meter and glucose the strips, right? Just put a strip here and you can see the number. But how the strip works? The strip is a sensor, a chip, lab on a chip. That's what we call here. And this is like a simple, a very small chip, like looks like this. So this is a small, like less than credit card size of a chip. that can be incorporated into the device here, but in the chip where we are embedding the nanoporous material. So the nanoporous material, when these molecules of water containing different contaminants and PFAS go over it, this, because we have the functionalities of nanoporous materials, specifically capture the PFAS, then immediately then there is a current change in the current happens, thereby giving it the impedance and giving the number of the sensitivity. With this technology, we could able to, so initially when we started, we could able to achieve like parts per million level. Then we modified the methodology of like how the water flow happens, the microfluidicity, and we worked around, went for parts per billion. And now in a stage right now, we can say that with this technology we can go up to parts per trillion level detection methodology. So you can go as like as low as the detection of parts per trillion, PPT, or nanogram per liter with this device.
So this is fascinating. So we've talked about what nanoporous materials are, and we've talked about the host-guest relationship between the PFAS that interact with those nanoporous materials. And so now it's actually been functionalized in this lab on chip setup. So you have water flowing through the material, PFAS interacting with the nanoporous material, and that creates an electrochemical type response. Is that correct?
Yes.
And so is it electrochemical impedance or electrical impedance that's capturing the detection?
Yes, I think I want to show you as a different slide where that impedance can show with simple analogy here. When you look at this electrode platform, okay, there is a strong current is happening all over because there is everything is fine. This is the capture probe here, the nanoporous material. When analyte is passed over on the capture probe, there is a attraction of the guest into the host, right? Then there is a change in the current, the impedance in the current happens. That impedance, how much impedance happened, is a measurable for us to go into the detection limit.
So how quickly does that occur? So we're talking, very low detection and concentration limits. I mean, how quickly does this reaction occur?
Yeah, that's a very good question. So generally, if you look at what are the current technologies are taking, right? So because of the low concentration, parts per nanogram per liter or parts per trillion, the people are taking days because to evaporate water or multiple MSMS technologies. But our technology, within 30 minutes, we can get the results. So frankly speaking, within few minutes, we'll get the result, but we were waiting for 30 to 40 minutes to stabilize the result, whether the impedance is right. That's what we are getting within minutes, say we can less than an hour.
So I think that's a huge breakthrough. I mean, very sensitive detection limit, rapid rapid detection to replace, something that could take days. I know in my field, you have some real practical limitations when you're doing field work, for instance, where you need to understand what's the concentration of this material before I can know what to do with it or how to dispose of it. So a huge breakthrough there. So could you talk to me about the specificity? Does this detect individual PFAS molecules or PFAS as a family of molecules? Can you talk about the specificity, please?
Yes. So as I've showed you in the other slide, how the PFAS molecules look like, right? Not only fluorine containing a fluorine on the top of the carbon chain, but also acetic acid, COOH, or SO3H, sulfur containing compounds. So when we engineered our material, if you have a material that can take all the fluorine, that is a possibility. But our intention is that when you look into all the PFAS concentration around the world, the one of the major contaminant is PFOS and PFOA. These are the two major contaminants, and PFOA is the top most contaminant of the PFAS family, a group of chemicals. So our intention is to tackle that one first. because that is a higher, wherever you can see the water concentrations, the PFAS concentrations in the water, the PFOS is on the top of the list. So our intention is to start with that. And we developed this nanoporous material specifically for PFOS. And we showed at parts per trillion level or nanogram per liter. Almost we showed at 5 nanogram per liter or zero 0.5 nanogram per liter. That low we went there. Then we come to PFOA, because at the second second highest molecule in that group. Recently, we also showed a different nanoporous material for the PFOA. You may say that, oh, there are two different materials. Yeah, there are thousands of materials, or like not thousands, but hundreds of materials are available. So we have to have, in the family of PFAS, even we have to have a different materials, nanoporous materials. For one is for PFOA concentrated liquid versus PFOS concentrated liquid or PFBS concentrated liquid.
So again, fascinating research, and recapping it again. So we're using nanoporous materials that have a host-guest relationship, where PFAS molecules get situated in those pores, and there's an attraction there. But you're able to, functionalize a sensor by applying that nanoporous material, to this fluidics pathway, and it's rapid detection, highly sensitive. We're talking low nanogram per liter concentrations, and it can be functionalized to specific PFAS molecules, PFOS, PFOA. I agree with you; those are the ones we're probably most aware of, and the ones we're most concerned about. Although we all know that there are thousands of PFAS out there. So very, very interesting and very fascinating. Could you talk, stepping back from the technology itself, could you please talk about the technology readiness level? Is this at the bench scale, or is it ready for commercialization? Where is it in the process?
At this point of time, like when we started in the PFAS work, of course, it's on the laboratory scale level and on the benchtop. So if you look at right now, or maybe like a year back, not right now, but a year back, it is all over half of the lab space, like table bench space, with a impedance analyzer, with the microfluidity and the sensor, the device, and all together. Like if you look at enter into the lab, like offside half of the lab is equipped with all those systems and everything. But that is not going to work for real world application. We cannot carry all over those things to the field and
Mm-hmm.
see the water. Only the thing is that you have to bring the water to test it, which is already the existing technologies are using. So our intention is doing the prototyping. So that's what I showed in the first slide, where we can have a prototyping. Having a handheld device with a laptop in backpack is sufficient. So at this point of time, while we are talking right now, just last week on September, we completed the prototyping, the box, the printing of the box, and manufacturing of a box, which is less than, like I can say, like with my hands, right? Just less than the small size I can hold with my hand. Complete system from the from in analyzer, electronics, all electricals, and the fluidics and the reservoirs, everything together into a small box that when they connected with a laptop, I can go into the field. That's what we are at this stage now.
So that was recently completed?
Just I think this week.
Okay, so on the verge of, prototyping a form factor of a fairly manageable size that can execute that whole process. That's extremely exciting. So Rod, how would you envision the useful application of the device, in the environment or an industry?
This is a very good question, because there's a lot of things has to be done in the PFAS science, especially in the detection space too. So, for example, this device, there are two things, as I mentioned, that the sensor device and the sensor chip, right? So how we can improvise on the device, which is, as I mentioned, like going from a bench top, completely occupying the bench top, to a small factor of holding a box.
Mm-hmm.
Are also working on the chip design. Why? Because the chip, which though it's less than a credit card size, but it is now taking a PFOS. But tomorrow, if I go to a field, there are multiple PFAS are there. So our intention is to have a connection between the chip to chip in a parallel or in series, to see whether we can having a chip A with a PFOS containing material, chip B PFOA containing materials, chip C a different PFAS molecule containing meaning that captured material, so that we can capture all the PFAS in the field. Say in a one site A, we have more PFOA concentration. Site B, there's another concentration. Can we just replace the chips or arrange the chips in such a way that we can do all those things? Second thing, my vision is having a telemetry on the box, meaning that I don't want to go like every day there, like 10 miles into the field and getting the testing. Can we have a telemetry? Can we have a Wi-Fi ability? And the battery, we are talking to the battery people, where that battery can last for a long time, and the Wi-Fi ability, so that I can sit on my computer and just push a button, or automatically can see what is the concentration. If there's a flow of water coming from a river, right? So I have to see the PFAS concentration today, maybe evening, maybe after 24 hours, after 48 hours. No need to go there. Having the chip, taking a small drop of water into the chip and test it and get the number here. That's what our vision is. And the third vision is by understanding the concentration of this PFAS molecule, one PFAS molecule here in this site A versus site B, and how the concentrations are going up, down, and putting into the machine learning or artificial intelligence to see the mapping of the total concentration of PFAS coming in this area, all those things, that is our vision, to go into the beyond, not only just for detection, but detection with telemetry, with AI, and all those things together, to have to tackle the problem in a bigger fashion.
So I definitely agree and identify with that. I mean, that's the beauty of electrochemical sensors is you're basically capturing an electrical signal. In this case, the impedance of that signal that can be integrated with microelectronics, and then you've got instant readouts and telemetry, et cetera. So I think that's one of the beauties of that type of detection technology. I like what you said about the amount of data it would collect and the prospect for artificial intelligence and machine learning. That's something I'm particularly interested in. We're collecting a lot of PFAS data as an industry, whether it's through conventional analysis or through this type of electrochemical analysis. And when you're trying to understand a problem, you collect a lot of data and you take a lot of measurements. But with those accumulating databases, I think there's definite potential for machine learning and gleaning more information from that. So that's been a fascinating discussion about the detection capabilities using nanoporous materials for PFAS. I want to switch gears a bit. We've talked about the versatility of this material and that it can be used for more than just detection.
Yes.
So I understand that it can be used for capture, and that can play into destruction. Could you please speak about some of the other uses of the material, such as for capture?
Yeah, exactly. Wow, that's a good question. So the detection, once we have the detection, the next step is to capture. Yes, I have the site A with concentration of this nanogram per liter, and site B has this nanogram per liter. Yes, but what are the current methodologies? Right now, people are using chemical beads, or like a activated carbon, GAC, or other porous materials already. But the problem with them is that if you look at a GAC, or granulated activated carbon, the problem is with that is that the materials are having low surface areas and low sorption capacities and slow kinetics. how can we construct these high surface area materials, the metal organic frameworks, the covalent organic frameworks, what we are constructing. We go a surface area very high. The carbons right now they're using is surface area of 200 to 500 meters square per gram of material. Even that, just to take a gram of material, the surface area is 200 to 500 meters square per gram. But we engineered the materials, nanoporous materials, that can capture 10 times, like 2000, 3000, 5000 meters per gram.
Yeah, that's amazing. I mean, I think, a lot of people in our audience are familiar with granular activated carbon, and they view that as a high surface area material. But you're saying, compared to nanoporous materials, the nanoporous materials are have a much higher surface area.
So even the carbon, the activated carbon also come under nanoporous materials, one class of nanoporous materials, because they are porous materials, right? The nanoporous materials is a bigger class, bigger family, where the MOFs and COFs are one kind of family, the carbons are one family, but
Okay.
low surface area. Even the zeolites, we can go up to 500 to 600 meters per gram. But MOFs specifically are COFs, covalent organic frameworks. We are engineered so that they have very high surface areas. Then you may ask, okay, you increase surface area from 200 to 5, or from 200 to 500 to 2000 to 5000. What is the advantage? Right now, so the advantage here is that by increasing surface area, you're accommodating more number of molecules inside. Right now, we are talking about tons of carbon. From there, you can just make kilograms of MOF sufficient to take out the PFAS into a small quantities that can be handled easily. You may say, why? What is the problem having huge piles? Because the third part coming to the picture is destruction. How to handle a 1 ton of activated carbon having the PFAS inside. The same thing, how to handle, when you compare to that, can we handle easily with 1 kilogram of MOF, which having high PFAS content. So handling is easy. You cannot put 1 ton into a body of like destruction, right? Is easy to handle. The second thing is that the activated carbon is not good for the smaller chains. As I said, PFAS are more than 5,000 at this point of time, right? So the activated carbon is good for the longer chain, PFOS, PFOA, but it's not good for PFBS or PFBA or smaller chain. Then what's happening is that in a field where there's PFBS, PFBA more concentration, then they're not taking much. And having the slow kinetics is another problem, taking very long time to get into the pores, because those are not engineered. These are just formed as is, right?
Mm-hmm.
Now, engineered having the specific functionality inside can improve the kinetics like very fast, can tackle the smaller chain, can tackle the longer chain, everything. That
So
is the
I,
advantage of our materials of for the capture compared to the
yeah, so I
carbon.
think that's pretty fascinating. I mean, I think people are definitely looking at ways to consolidate, to concentrate, to reduce those waste volumes, and it sounds like there's definitely a role there for um, nanoporous materials, especially some of the more specialized ones you mentioned, metal organic frameworks, the covalent frameworks. But yeah, something that can be engineered or tuned to those shorter chain PFAS, your PFBAs, your PFBSs, the ones with 4 carbon backbone. That's definitely a challenge using conventional materials like GAC. So that really piqued my interest when you mentioned that.
Mhm.
Fascinating.
Thank you.
So that's a great discussion on, the capture, the sequestration of PFAS with those nanoporous materials. Can you talk to me about what you're looking at as far as their role in destruction of PFAS?
Yes, the destruction. So the capture in these three detection, capture, and destruction, we are way ahead in the detection and working hard to get a capture also. And destruction we just started lately. Since the engineered nanoporous materials like MOFs showed very good adsorption at gaseous phase fluorocarbons already, we want to use the material for gaseous phase adsorption in the incineration process. Because why the most of the states are not allowing incineration? Because it's forming the nano gaseous PFAS, right? There we can use the nanoporous MOFs that can take all the can capture all the gas phase PFAS. That is the primary. The second thing is that instead of going to incineration, can we go lower temperature destruction? Can we do that? The possibility is that the nanoporous MOFs can be used for catalysis, because a couple of my projects I'm also working on the catalysis work, where conversion from A to B, catalysis. There we can we decrease the temperature from 900 to 200, 250, or like 150 by catalyzing using the catalysis process. How that can happen? Now as I said, the fluorine is inside the pore, now elongating the CF bond by the functionality in the MOF so that you can break the bond. That is our thermocatalysis way to destruction of the PFAS. That's what we're working at this point of time. So PNNL is putting a lot of efforts and money to develop all these technologies of the detection, capture, and destruction, where the destruction is a little bit behind, but we are working on the thermocatalysis way. And also, if people wants to continue with incineration, capturing the gaseous phase PFAS, both.
I think that's fascinating. And as I started out with the podcast, especially interested in your work and nanoporous materials, because it's hitting the three themes of this podcast for detection, destruction, and capture or sequestration, however you want to describe it. But I think that's very interesting about how it could enable or make incineration more effective, which can be problematic at this stage, or lower the thermal temperature as low as you mentioned. So sounds like PNNL is making great strides in all three of those areas: destruction, capture, and detection. So kudos to you and your team at PNNL. So Radha, is there anything else you'd like to tell us about your research or your technology?
Yes, one thing I want to tell you here that since PNNL is a national laboratory, we are working on the technology to technology transition level at higher level that industry can take into, because in PNNL can never produce the device or sensor, chip or whatever. This only the development can happen here, where we are working. Our PNNL is working with the industry partners to make taking a license, giving a license to our technology to make them to available for the public. That's what technology transition will happen from a national lab to industry.
Okay, I think that's very good to know. Solutions coming out for this challenging problem, and also opportunities for industry.
And
so,
DOD is sponsoring a project to PNL on the detection of PFAS. So they are interested in 6 different kind of PFAS molecules. Right now we showed only 2 or 3, but they're interested in 6 containing 6 PFAS molecules. So we are working. This is a 3-year project. We are working with on the DOD project, and also PNL is putting a lot of internal funding for the capture, destruction, and detection, the prototyping and other things too.
Outstanding. Well, that wraps up this episode of the Disrupting PFAS podcast. Thank you to Dr. Radha Motkuri of Pacific Northwest National Laboratory for joining us today. I'm your host, Jeff Hale, reminding you to never say forever.